All right, chapter 18, sampling distribution models. So sampling distribution. It shows the behavior of a statistic over all the possible samples of the same size. Every random sample will give a different value for a statistic. A sampling distribution model lets us talk about how likely it is that we would observe a sampling proportion in any particular interval. Just emphasize it. Because it's just kind of saying like what that's helping us to do or to find. Sampling distributions are based on the normal model and are specified by two parameters. So mu is the mean and sigma the standard deviation. Now mu, the mean, is set at P, which is the population proportion. And this proportion means we are dealing with categorical data. Now, p hat is the observed proportion in a sample. And the standard deviation of p hat is equal to the square root of npq divided by n, or we could say that it is the square root of PQ over N. So just like in the last unit, we also have some conditions here. So for using the sampling distribution model, we have an independence assumption, which says that the sample values are independent. We have a sample size assumption, which says that sample size N is large enough and then we check the conditions. So those other things are more assumptions. These are the conditions that we're checking. The first one is randomization. Data gathered randomly. The 10% condition, which is that N is less than or equal to 10% of the population. And 3, success failure. So these will look pretty similar to what we had in the last one. At least 10 of each. So NP is greater than or equal to 10, and NQ is greater than or equal to 10. So sampling distribution model. For proportions, provide sample values, or provided, I should say, sample values are independent. And the sample size is large enough the sampling distribution of p hat is modeled by a normal model with the mean, mu of p hat being equal to p, and the standard deviation of p hat being equal to the square root of pq over n. Huh? A pen? Oh, I thought you said a pen. I was like, don't you have a pencil? That's fine. The next thing's an example, so I can hold for a second. got it? Okay. Apparently I'm coming back to help at basketball practice today.
So,
Apparently I'm coming to help at basketball practice today for the girls. I don't know what I'm doing, but apparently I'm coming to help, so. All right. So I have an example, so I'll write out the example and then we'll kind of walk through it a little bit, but 13% of the population is left-handed. Hey, you're one of those 13%. A zoo, wait, nope, sorry, not a zoo. A 200-seat lecture hall. My 2 looked like a Z, and I thought I just forgot to put the line through it. Has been built with 15 lefty seats in a class, or I guess this is the question, in a class of 90 students. What is the probability that there will not be enough lefty seats? Have you had a lefty desk before?
yeah, it's like when this parties on this side.
Yeah. We used to have like 2 that were like folding ones so that like they could use them like upstairs or whatever, but they were like smaller, so it wasn't really that useful, but
I never had one.
you've never used one? I don't even know if we still have them. Ours were literally like those folding chairs, but they had like the arm that came down like a normal desk. So they just weren't very big, but
Yeah, I never had that.
most of my friends that like were left-handed were like, yeah, they're not really like, I don't want to say not useful, but they were just so used to a regular desk that it wasn't like anything special for them.
That's how I would imagine.
Yeah. Like my dad's left-handed and he said that he's had a few in his lifetime of like they're actually like spiral notebooks that are like for left-handed people.
Yeah, I never heard.
So I don't really know. I don't really understand, but like the spirals were like on the other side. So it's almost like using the book backwards. Or they would get the ones that were like the spirals were at the top
Yeah.
so that they didn't have to like write over top of the. Like being left-handed, like writing on a board, it's pretty awful. Or at least so I've heard. I mean, I've tried a couple times, but I'm not really left-handed, so.
My mom was left-handed, but she switched to right.
Did something happen that led her to switch? Like, did she like break her arm and then she just switched, or she just learned to do it right-handed?
Her mom, my grandmother, she was just like, I guess they saw left-handed people like as like a deficiency, so she had to rock with right hand ever since, and she said she regretted it.
Yeah, there's a lot of stuff that it's like I don't think people understand like how good it is to be able to either use both or like to be left-handed, because like everybody like goes right, like that's just like the natural thing to do. So yeah, my dad can do both pretty well. I learned to do both when I broke my arm, but it's not as pretty and it takes me way longer to write. Okay, so in a group,
And she told me the story of Eva or Ava, whatever you want to pronounce it, in the Bible. And then she been telling that story for like the past 2 years. It's a fascinating story, but I get it. He was left-handed, you know.
that's funny. In a group of 90, 15 out of 90 is 16.7%. So we need to find the probability of finding more than 16.7% lefties if the actual population proportion is 13%. So check the conditions. Here I'll actually write them out. Pretty much from here on out, I'll just mark that we did check them without actually writing them out. But independence, the probability.
So it's the same thing as the 10% condition, right?
Technically, no. So in the last chapter, we were saying that they either had to be independent or it had to be the 10% condition. We are assuming 10%. We're assuming independence here. But the 10% condition also has to take place in this one.
So in this case, 10% has to, but in the other, it was just assumed. Did I say that right?
Yes, I think so. I was trying to think. So basically, the other one, it had to be one or the other. If you didn't know if it was independent or not, it had to be the 10% condition, or like vice versa. But in this one, we're assuming that they are independent, partly because of what we're working with. So like left-handed or not, like that's a categorical variable. So that's part of it. So like, either you are left-handed or you are not. And you being left-handed doesn't affect if I'm left-handed or not. So we can assume independence on that front, but then 10% is of the entire population. So the probability that one student is a lefty is not changed by another student's left or right-handedness. As far as randomization, 90 students can be considered a random sample. And we may not be able to prove that directly, but like 90 students out of all the students in a college are probably going to be pretty random if it's in like a big lecture hall like that. So then the 10% condition, 90 is much less than 10% of all students. And then checking for success failure. And a lot of times I will end up just writing that as SF for success failure, but N times P is 90 times 0.13, which comes out to be 11.7, which is greater than or equal to 10. And then N times Q is 90 times 0.87, which is 78.3, which is also greater than or equal to 10. So that's met. So I'll let you get that, and I'll keep going. Okay, so based on that, the conditions are met for a normal model. So we state the parameters. So P is equal to 0.13, so that's the success, is that we find a left-hander. So the mean of P hat is 0.13. The standard deviation of P hat is equal to the square root of PQ over N, which is the square root of 0.13 times 0.87 divided by 90, which is 0.035. So we're using the normal model of 0.13 and 0.035, so this is just mean and standard deviation for the normal model. So I'm going to draw a little curve here. With the mean of 0.13. Now they told us that 15 over 90 is 16.7%, so we need to find the probability that of more than 16.7% are lefties. So that means that we're looking at this value over here for 0.167, which is P hat. So this area here is telling us the probability above 16.7%. So there's a formula that you're gonna need just in general. I don't know if it's gonna get written anywhere else, so I'm gonna emphasize it here, but Z is equal to P hat minus P divided by the standard deviation of P hat. So P hat is the observed. So in my case, that's going to be the 15 over 90 number. P is expected, which was 13%. And then standard deviation is the square root of NP over Q, or wait, sorry, wow, hello. PQ over N. So this is just a formula that I would just make sure you know. This is to find a Z-score, which would then use a table, which is something I'll more go over when we start reviewing for the AP exam, because we usually just do it on the calculator. So.
As soon as you say my heart just dropped.
I mean, you've got
3 months.
yeah, 3 months, almost exactly. Hopefully we'll be done in about 2 with everything. That's the goal. And then we'll have a month to review. Last year, because we were like kind of behind, they were literally coming in at 7 a.m. every day to review with me.
They told me, like, I think Taylor told me that last week when I was studying for the test. She was like, at this point, y'all was like at chapter 12.
Yeah, because we had so many quarantines last year. It was pretty rough. So if I were to do this for this problem, just so that you've seen it, it would be 0.167 minus 0.13 over 0.035, which is 1.06. Then we would do, it's the probability of z being greater than or equal to 1.06, which would come from a table, and I'll show you what that gives you in a second. But we can do the calculator way that we were doing before with normal CDF. So I would just do normal CDF of the lower being -1 e to the 99. Wait, brief pause. Sorry. Hold on. Normal CDF, I'm going to do it for our actual scenario. 1.06, no. Yeah, we use this value that we found. 1.06, then you can go up to whatever. You can say 1E99 if you want, or you can do something smaller because there's a point where it'll never actually reach it. Then 0 and 1 because we're using the normal model. Let me check and make sure that's right. Oops. Nope, not that. Normal CDF. And that gives you 0.1446, and that would give you the same thing from the table as well if we went and found it. So you could have even really used like the number 10 here because you have such a small number you're working with that's going to be so far away that you could use that, but I would just stay with the 1E99 just because that's what you're used to. And then so to kind of conclude this problem, there is about a 14.46% chance that there will not be enough seats for left-handed students. We might actually be able to power through this all. It was only 5 pages, and like the last page is only like a half page. It's really only like 4.5 pages. We're already on page 4, so. And we have 15 minutes, so we'll see. I kind of thought so. Well, at first I thought I heard Will's voice, and then I was like, that's not his voice. All right, this.
It's not that bad so far.
Wait till she grades it.
Yeah, that's scary. People say that she grades it.
But usually, if you've done your stuff the way you're supposed to and on time and all that, a lot of times she will let you correct so much like of whatever she's marked as like wrong and get like half credit back. So like if you got an 80 to begin with, you theoretically could finish with a 90. So if you fix everything the way that she wants it fixed.
How much is it weighted for like the marking at a quarter?
I think it's a test grade.
The test grade?
Like, I think that's, like, what it equates to, but I'm not 100% sure. But it's technically 2 test grades because it also counts for history.
Oh. So it's like...
And it probably won't go on till 4th quarter because they probably won't be graded before 3rd quarter's over.
So it's probably 40%.
Yeah, but it would like roll in with all the other test grades that you have. So, I think I could be wrong about how she does it, but all right. This next concept is a big deal. So, the sampling distribution of any mean, and that's talking about quantitative data now, becomes more nearly normal as the sample size grows. The only conditions are observations are independent, and observations are collected with randomization. So the next thing we have is the central limit theorem. And you'll see that written as CLT. And this is the mean of a random sample is a random variable whose sampling distribution can be approximated by the normal model the larger the sample, the better the approximation will be. The conditions for this stuff are basically the same. As for sample proportions, there is an independence assumption and a sample size assumption. And then the conditions to check we have randomization, we have a 10% condition, and a large enough sample so there's no NP or NQ here. So we have to consider your context, which is what shape is the population, finally on the last thing. Sampling distribution model. For a mean with the central limit theorem. When a random sample is drawn, from any population with mean mu and standard deviation sigma, its sample mean y bar has sampling distribution with the same mean mu, but whose standard deviation is sigma of y bar is equal to sigma divided by the square root of n, which is the standard deviation of y bar. So no matter what population the sample comes from, the shape of the sampling distribution is approximately normal as long as the sample is large enough.